Hey QED coders, this is Michael. Now I'm sure you're wondering why I call you QED coders. That's because QED is what a mathematician writes at the bottom of a proof, and your code should be so good that you can write QED and know that it is correct. And that's what QED code is all about. And I want to help you to become a QED coder with respect to distributed systems. Hi, I'm Michael L. Perry. I'm an improver from the Dallas office. And on the call, we have Michael Slater from the Houston office. And he's going to be taking your questions. So please go ahead and type those into the chat window as we progress today. And if one of the questions is really important, really relevant, and we need to answer it in line, Michael will go ahead and interrupt and give me the question. Otherwise, we'll save those questions till the end. We'll leave about 15 minutes of question and answer time at the end. So please enjoy as we talk about ACID 2.0. So this is all about building reliable distributed systems using the fundamental principles of mathematics. So if you're familiar with database transactions, you've probably heard of the ACID properties. So these are atomic, consistent, isolated, and durable. So the ACID properties are promises that a database gives us that then as we build applications, we can depend upon. So atomic, for example, that means that if the transaction succeeds, then everything is written. But if it fails, nothing is written. It all rolls back. Consistent means that between transactions, your application invariants are upheld. So if your application is a financial application, for example, one of your invariants might be that money is not created or destroyed. And so that's consistent. Isolated means that if somebody else is performing a transaction at the same time as you, then they're not going to see any of your changes until you've committed, or you won't see any of theirs. So if they start after you've committed, then they can see everything, but if they start before, they see nothing. And then finally, durable. That means that if the transaction commits, everything you did is written to disk, and when you come back, it's still there. So you might say, well, of course, I need a database to be ACID in order for me to build a correct application. How could I build an application on top of a database that doesn't give me these guarantees? And for the longest time, that was absolutely the case. But then distributed systems became a lot more popular. And then we had distributed transactions where we had to make sure that two or more databases were kept in sync. And the problem with distributed transactions is if you have these ACID properties that have to be upheld at the database level, that means that they need to span across multiple databases. So you have to be atomic across two or more databases. If you write something to one database and another, and then the other one fails, you have to roll back the first. You have to be isolated so that if somebody is reading from one database and that's going to be part of your transaction, they're not going to see what you're doing, even if you're still working on another database. So the problem becomes much more difficult when we're talking about multiple databases. So lots of different companies have worked on distributed transaction coordinators. In particular, Microsoft is a vendor of a distributed transaction coordinator, DTC. And one of the people who helped to build that DTC was Pat Helland. In 2009, Pat Helland had a bit of a reawakening. He noticed that applications and database systems in particular were doing a lot of work in order to guarantee the ACID properties of distributed transactions. And all of this complicated mess, it had all sorts of different edge cases, and you could make it work 90, 95, 99% of the time. But he recognized that the guarantees that you were getting were still probabilistic. It was very difficult to guarantee 100% ACID properties of a distributed transaction. And so he recognized in 2009 that perhaps the applications are requiring too much of our databases. And perhaps it's possible for an application to not need the ACID properties, but instead rely upon a less restrictive set of properties. And so he wrote this paper, Building on Quicksand, where he's talking about how the network of a distributed system is shifting underneath our feet. And so we need to build a reliable application on top of it. And could that be possible? How could that be possible? In this paper, he identified 4 properties that if an application has these 4 properties, then it could be built on top of a shifting, unreliable network system. And so that's the idea of building a reliable, solid application on top of this quicksand. And so he gave those 4 properties the name of ACID 2.0. And that's because, as it so happens, he was able to find 4 properties that had the acronyms ACID. And so that's what we're going to be going through today, is we're going to study each of those 4 properties, and we're going to see how you can build your application to have these guarantees built into it so that you don't rely upon a database having the ACID guarantees. So, it's off. There are 2 hard problems in distributed systems. 2, exactly once delivery. 1, guaranteed order messages, and 2, exactly once delivery. Now, this is one of many variants on the 2 hard problems set of jokes, but this one I find to be really poignant and really describe the difficulty of building a distributed system. It's really difficult for the underlying network infrastructure to guarantee that messages are going to be delivered exactly once. It's also very difficult to guarantee that the messages are going to be delivered in order. In order to provide those guarantees, it basically has to serialize the messages and say, all right, I'm going to send this one to you. Did you get it? Okay, you did. Now I'll send this one. Did you get it? Oh, wait, no, let me try again. Oh, I just did multiple delivery. Okay, I have to make sure that it's not processed twice. It's a very difficult problem for the network infrastructure to solve. So what if we built applications that did not require these 2 properties? If it did not require exactly once delivery, we would build an application that was idempotent. So you might have heard this term in relation to HTTP verbs. So you might have heard that a post is not idempotent, but a put or a patch is. So I'll demonstrate what idempotency is in terms of an HTTP API. If I were to get a resource, say people/42, and I get back the object with the name Bob, now let's say that I put a new version of that resource, name Robert. Now what's the value of the resource? It's name Robert. If I were to put to people42 name Robert again, what would you expect to happen? Well, put is idempotent, so that means that it won't change the state of the resource. It's still going to have the name of Robert. So idempotency helps us to tolerate duplicate messages, and we no longer need exactly once delivery. That's a great way to build your applications. Now, what about the out of order transactions, the out of order messages? Let's suppose that I've got an application where it's a game and I'm scoring things. Maybe it's like a Boggle or a Scrabble game or something like that. And so I make a move and I score 3 points, and now my total score is 3. I make another move and I score 5 points, and now my total score is 8. If I wanted to tolerate out of order messages, I could make my application commutative, so it doesn't matter what order those two messages arrive in. If I were to score 5 points first and then score 3 points, I would still have 8 points. So an application that's commutative, that helps me to tolerate out of order messages. And you might recognize that this is actually just taking advantage of the commutative property of addition. A plus B is equal to B plus A. Commutative, idempotent, these are just math words, and we're applying them to software, QED. But the problem is some things that are idempotent are not also commutative. For example, HTTP put. If I were to put to the resource the name Robert, the message would be Robert, but then I come back and put to that same resource the name Larry. And now the name changes to Larry. So that's how put should behave, but what would happen if those puts got sent in the opposite order? I would end up with a resource with name Robert and not name Larry. So the order matters. And if the order matters, then my application is not commutative. So it can be idempotent, but not commutative. What about the other way? You can make an application that is commutative, but not idempotent. So my scoring application. If I score 3 points, my total is 3, and then I score 5 points, my total is 8. So we've already seen those operations are commutative, but what if I were to tell the application again that I've scored those 5 points? If it gets my my total score up to 13, then it's not being idempotent, it's just being commutative. So in order for me to tolerate out of order messages and duplication of messages, I have to be both idempotent and commutative. Okay, so those are going to be very important properties. That'll get us past those two hard problems. But there's one other thing that we do in distributed systems, and that's that not all nodes receive all of the messages. Sometimes we aggregate things. So if you've got, for example, a reporting database, and you're going to take all of your individual transactions for the day and then periodically send a batch to the reporting database. So here you go ahead and apply all of these transactions. Process a few more, send another batch. That's a very efficient way for a distributed system to work. If you had to send each individual transaction to your reporting database, then you would be spending a lot of money making sure that that thing stayed up to date when you could be saving yourself quite some money and making it go faster. So you batch things. You want to make sure that no matter how you end up batching them, that the final result is not sensitive to the grouping. So if you were to send a batch of 3 and then a batch of 2, you should end up with the same answer as if you sent a batch of 1 and then a batch of 4. So no matter how they're grouped, you need to get to the same answer, and that is the associative property. You might recognize that from mathematics as well, where you can put parentheses around different parts of your expression. Like you can add 3 numbers together and then add 2 numbers together and add the result. That's the associative property. All right, so we just talked about 3 really cool math words. There's one really awesome math word that that combines these 3 things. So if you'll forgive me, let's really geek out here. So the associative property, we can write that by saying that we've got y and z in parentheses and then apply x, or we can put x and y in parentheses and then apply z, and we get the same answer. So we can write that little equation. That means the associative property. The commutative property, x and y can be swapped, and the idempotent property, that means that if I've already applied x, if I apply it again, I still get x. I still get the same answer. So we can write these as equations, and if a mathematical operation supports these 3 properties, then it's called a semilattice. Now, You might think, okay, this is just mathematicians making up words, and yeah, to be fair, mathematicians do make up words. But this one, I think, is actually a very appropriate word for what it is that we're describing here. It's kind of hard to see from just these equations, so let me show you what you can think of a semilattice as. If you were to take a value, say x, then you could look at all of the possible values that you might end up with by applying this operation with other values. So you can think of this as all of the possible future states of the thing that started at x. So you could, for example, combine it with y. And then the first time that those two future cones intersect, that's x with y. So that's the point at which these two future values converge, and now the entire future from that point includes both x and y. I know this is pretty abstract, so yeah, I wouldn't fault you for thinking, you know, there's probably, you know, more to this than this, or what could I possibly do with this? We're going to get to a concrete example in just a second, but I want you to really appreciate one of the things that's going on here. This value that you get when you combine x and y, you could think of combining as addition, although addition does not follow the idempotency property. When you combine x and y, that first value that you get there, that's the very first value that includes both x and y. And that has a very special and very important name. That has the name the least upper bound. Why is that? Well, the future cone of x and the future cone of y, all of those values are in some sense greater than x and y. So x combined with y is greater than x and it's greater than y. It's greater than both of them. But there's no lesser value that is so. So that's the least upper bound. Starting to make a little bit of sense? Okay, well, let's throw in z there. And now we can start to see how these three properties give us a semilattice. So x combines with y combines with z, and then when those two cones intersect, you've got x, y, and z all together. And so you can see that if you get there through the green side, then you're following the right-hand side of that first equation in associativity. You're taking x and y, and then you're combining z, and you get into the orange at the top. But you take the other path. You go through z, and now you've taken z and x, or z and y together, and then you're combining x. So you're taking the left-hand side of that associativity equation. So you can see that this picture is starting to give you kind of an intuitive suggestion of what associativity really means. The associative property, the commutative property, and the idempotency property all give you this this kind of a system that has a least upper bound, and it has things that are strictly greater than the thing at the point. And now that we see this picture, you can see why it's called a semilattice. You can kind of see that lattice structure in there. It's called semi because these cones are open at the top. If we flipped it and we had cones that were open at the bottom, that would be a different kind of semilattice. A lattice would be closed at the top and the bottom. It would look like a whole bunch of diamonds. So, you know, go out to your garden, take a look at the trellis. Well, that's a lattice structure. Semilattice is just a mathematical system that supports that structure. So, thank you for letting me geek out with you for a second. Now, how do we actually use this stuff? If you were to take a look at sets, when you do a set unions are associative, they're commutative, and they're idempotent. Let me show you an example. Let's suppose I've got a set that has a car, and then I union that with a set that has a bicycle and a train. I get the set car, bicycle, train. That's the set union. I could have built that same set with car, bicycle, and then train. So it doesn't matter how I've grouped things together. The set union ignores the groups and it follows the associative property. So set union is associative. Commutative. If I take a car and a bicycle, union them together, I've got the car bicycle set. Or I could say bicycle union car, and I get the car bicycle set. And that's because sets don't preserve order. It's just something's in the set or it's not. And so sets, and in particular set union, supports the commutativity property. So set union is associative, it's commutative, and it's idempotent. You union a set with itself, you get back the same set. The things that are in that set are already in the set, so doing it a second time doesn't change anything. Sets don't keep count of how many things are in them or how many copies of a thing are in them. It's just either in or it's out. And so because of that, sets are associative, commutative, and idempotent, which means that set union is a semilattice. Okay, so that's a bit more of a practical example of what I mean by semilattice and what I mean by associative, commutative, idempotent. Now, what does that have to do with software? Well, if you think of a database is a set of records. So what if I treat my database as a set? And the only operation that I allow is set union. So that means I could never have two copies of the same record. It's just either there or it's not. And it also means that I could never remove a record because all I'm allowing is set union. It would also mean that I could never modify a record because I'm not allowed to take one thing out and put a different thing in. I'm not allowed to change the values that are in the set. All I can do is union more. So any database that only allows inserts, never update, never delete, that is using a set union, and that's a semilattice. And so that gives you the associative, commutative, and idempotent properties. So I just think that stuff's so cool. I hope you do too. So we've got three of these things, and you'll notice, hey, the first letters are A, C, I. So we've got 3 out of the 4. What's this D in ACID 2.0? That's the distributed property. Now, I'm not talking about the distributive property. I know, mathematician here, you would expect me to talk about distributing multiplication over addition or whatever. But no, the distributed property simply means that if I were to take any transaction and apply it to any of my databases, no matter which database I choose, I will get the same result. So think about some of the distributed systems that you've come to know and work with. Some of them have this behavior that they elect a master. They decide, this is the node that's going to process all of my writes. Now, there's a good reason for it to do that. If it elects a master, then that means that that master can be in charge of conflict detection and resolution. It can make sure that that things are locked and that things become consistent. So basically, electing a master boils the problem back down to ACID. And it's not really a distributed system at that point. It's a single system, a single valued or a single node system that just happens to have multiple replicas. And you can read from those replicas. That's useful, but that's not a truly distributed system in this sense. So a distributed system, no matter which node processes a transaction, it's going to get the same result. So it doesn't matter where you send that transaction. And so that's what we mean by distributed when we're talking ACID 2.0. So ACID 2.0, associative, sorry about missing the E, associative, commutative, idempotent, and distributed. Associative, we can group transactions in any order and we'll always get the same result. Commutative, we can change the order of transactions and we'll always get the same result. Idempotent, We can replay messages, and we're not going to duplicate the effect. And distributed. It doesn't matter which node processes the transaction, it's going to end up with the same result. So those first three, as long as you're using a semilattice, then you're good. All four, that's ACID 2.0, and that's how we can build better applications. Now, I'll bet you that you're probably looking at this and saying, okay, that's a lot of math words. How can I actually apply this? Well, let's put this into practice right now. Let's walk through an example, and let's see if we can apply the principles of ACID 2.0. So let's suppose we've got an application and we need to create a person. You've got your mobile application, and it's using a REST-based API, and so it's posting to the people collection, and then the web server picks that up and it inserts something into a database, and then it uses identity in order to pull the auto-generated ID out of the database for the record that it just inserted. Now, it sticks that onto the end of the URL and sends that back in a 201 created response. So during this entire process, the mobile application is just spinning, waiting for this database ID to be generated so that it knows how it can refer to this object in the future. So this might look pretty familiar. It's a pretty common standard way of building applications, of developing REST-based APIs. And this is a perfectly correct implementation of REST, but it is not ACID 2.0. So this does not make for a very good distributed system. Can you identify which of the properties it does not uphold? So let's look at that list again. Associative. Can we group these people together in different ways and end up with the same set of people? Yeah, that sounds about right. I think we can. Commutative. If I were to send two different messages to create a person and just happen to send them in the opposite order, would I still end up with two people? Sure. Yeah, their IDs might be flipped, but the correct behavior of the application doesn't depend upon the order of the IDs, or at least it shouldn't. So yeah, this is commutative. Idempotent. We might have a problem there. And distributed might be an issue there too. Let's take a closer look. This API I specified is not idempotent. And here's why. If I were to post to the /people collection an object with name Robert, I would get back people and then some ID, say people 42. And then let's suppose that I missed that response. I just, I was using my phone and the train just went into a tunnel. So when I get out of the tunnel, I have to try that response again, or try that request again. If I do that, then I will end up with a brand new ID because it'll do a new insert, it'll do a new add identity, give me a new URL. And so this is not idempotent. My intent was to have one person, but my actual behavior is that I have two. So we're going to have to see if we can change this API, change the nature of this request so that we make it idempotent. But first, let's take a look at distributed. How is this not distributed? Well, let's suppose that I had two different replicas out there, two different servers that could handle this response. So rather than thinking about this as load balancer, two different servers that then talk to the same database. If you do that, you're pretty much a single source system anyway. But no, you've got two different databases. You might want to do this for just the simple fact of being able to write to multiple replicas really quickly in different regions and then aggregate those together later and share them out. So you might be doing that just to be more efficient. You might also be doing that because these two databases are owned by different organizations and they're going to settle up at the end. So sort of like reconciling their bank books. But whatever the reason, you've decided that your application needs to have two different databases, and the first time you send a post to people, you're going to get back people 17. If you send that same post to a different database, it's going to generate a different ID because these IDs are automatically generated based on how many records are already in the table. So you might get back, people 351. So it matters which one processes the transaction, which identity you get back. And more important, if you were to take this people 17 and try to send it to that second database, that would be a completely different record. That would be a completely different person. You would be mixing these things together. In order for something to be distributed, the identity has to not depend upon where it's stored. The identity has to be location independent. So if we are relying upon the database to automatically generate our IDs, and we're using those IDs as the publicly visible identity in the URL, then our system is not truly distributed. We're depending upon those locations. So what is the solution? Well, one solution is that we can simply put a resource to the desired ID. So we come up with the identity that we want this resource to have, and we put together that URL. So say I want to put, forgive the slide, that is supposed to be a put, not a post. So I put to people/Bob 1945, and the resource's body name Robert. And so then the identity of that resource is people Bob 1945. If I need to replay that message again, what's the identity going to be? It's still going to be people Bob 1945. So the identity no longer matters, no longer depends upon how many times you tried to post that message or put that message. So the identity is no longer generated by the server, it's generated on the client. Notice there also that the ID that I'm using, that's not just a number, that's in this case a username. So maybe this is a sign-up form where somebody is trying to create their own profile record right now. So they come up with the username that they want and then they try to put it. And you've got your security in there to make sure that somebody else doesn't have that ID already. So all of that stuff still comes into play. But the important thing is the identity was known before you made the call. And that way you can tell if you're receiving a duplicate. If you don't know the identity before you make the call, then the second call might be the same one, or you might just want to create a new object that happens to start out looking the same. So client-generated ID is an important way to solve this problem. But this doesn't just solve the idempotence problem. This also solves the distributed problem. It doesn't matter which node receives this request. It will generate an object that has the same identity no matter what, because the identity came from the request itself. So client-generated ID, use put and not post as it shows on the slide, and then you can solve the idempotent and distributed properties of the application. If you take a look back at the original problem here, notice that while we are waiting for that identity to come back, the phone can't really do anything. I mean, what's the very next thing that the user is going to do? They're going to probably take a look at a form that has that person's profile in it, and they might start editing that profile. pretty much no matter what the user is about to do, they need to know the identity of that person. If we're relying upon the database to provide that identity, then that means that the phone doesn't have it yet, and it has to wait. So we are forcing our users into this wait cycle by posting and waiting for the identity to be generated. But if the identity was generated client-side, we would know what it would end up being, and we wouldn't have to wait for it. So that not only solves the ACID 2.0 properties, but it also gives the users a better experience. So in this particular example, a great way to solve the problem with client-generated ID makes a better distributed system and a better mobile app. Pretty cool stuff. Okay, so kind of wrapping up there. Oh, there's the E. It ended up on the next row. The ACID 2.0 properties are that things are associative, that it doesn't matter where we put the parentheses, that it doesn't matter how we group things, we'll always end up with the same answer. And operations are commutative. That means that we can process those operations in either order, and we'll still get the same answer. And also that operations are idempotent. It doesn't matter if we receive the same message multiple times, we will still come up with the same result. Those three are satisfied by anything that is a semilattice. Set union is a good example of a semilattice. So if you build your applications such that it's just insert new records, never update, never delete, and you just use set union in order to merge from other nodes, then you get the first three just based on that operation. And by the way, that kind of a data structure is called a conflict-free replicated data type, CRDT. So those are really cool. If you want to do some more research, look into CRDTs. Those are semilattices. Those are just really, really cool data structures and really important for distributed systems. But they only give us the first three. That the last one, distributed, in order to make sure that something is truly distributed, you have to make sure that the way in which something is processed doesn't depend upon which node is doing the processing. So things like automatically generated IDs by incrementing a number, those make things specific to that location, and you're no longer distributed. So be aware of that. Be careful about that. If you want to, yes.
I have a few questions I'd like to interrupt you with.
Sure.
The first one is for a client-generated identity. How would you recommend dealing with collisions and uniqueness?
That's a great one. So, for example, let's take the username thing. So, when somebody generates a username for the first time, you want to make sure that that username is not taken, that somebody else isn't trying to use it. For that case in particular, the likelihood that somebody is creating that same username right now is pretty small, but the likelihood that somebody created it in the past is a bit larger. But still, even if somebody's creating that username right now, you want to make sure that you don't allow both of them to have been created. So sometimes you do have to step outside of the ACID 2.0 properties and instead go to ACID 1.0. You have to actually take a lock on a single master system of record in order to make sure that that username is not duplicated. So it's really a trade-off. If you're familiar with the CAP theorem, and we should probably do another one of these on the CAP theorem. That's awesome stuff. But that tells us that we can't be consistent. Goodness, I'm mixing up my A's now. Partition tolerant and available. That's it. That's the A. We can't be consistent, available, and partition tolerant all at the same time. When we are guaranteeing the uniqueness of a username, for example, we want to be consistent. We have to dial consistency all the way up to 10. ACID 2.0, it relaxes consistency and dials availability up. So the trade-off between ACID and ASCII 2.0 is really a trade-off between consistency and availability. And for something like that, you definitely want the consistency. You want to go to a central source, but make sure that you limit your reliance upon that central source just to guarantee uniqueness.
I think a follow-up question on the REST API portion was, will a put still allow you to overwrite a resource? Is it recommended for this to be immutable?
That's a very good question. The way that I like to take this all the way to the extreme is to, like you said, make things immutable. And so that means that that when I'm creating a truly immutable application, I'm that the only thing that's in the resource is the identity, nothing that could change. And then the thing that you would put, you would basically be inserting a new version of that resource. And so you can keep multiple versions, and you just want to refer back to which version it is you're replacing. So there's a whole bunch of detail we could go into about vector clocks and how to make all that happen. But yeah, that's not the end of the story with the puts.
Thank you for that. And I think to wrap up this section, are there any further questions I should be asking myself to determine if I'm modeling a semilattice or not?
Yeah. Yeah. So if you can kind of intuitively feel your way through the idempotent commutative and AC and yeah, the A is the one associative. Okay, yeah, the associative, commutative, and idempotent properties. Then those are basically the questions that you would ask yourself. Is what happens if I get this message twice? What happens if I get these messages out of order? What happens if I group them differently? So so you could get there just with that kind of intuitive feel and trying to work your way through problems. A more rigorous way of doing that is to really get into the mathematics behind it, to really get comfortable with writing and reading proofs, and that's not for everybody. That's something that I enjoy doing. A lot of folks enjoy doing, but you might not be one of those people that that likes to sit down and write a proof or read one, and that's fine. That's fine. You can rely upon kind of that intuition in order to give you that feel. The challenge is when you start to get multiple operations. So if all we're talking about is putting things into a set, just set unions, you're just dealing with one operation. You can intuit your way through that. You can get a feel for it. If you have a system where you need to update somebody's name, they need to be able to move from one address to another. You need to ship an order, know that it's been received. All of these different operations, and you need to intuit your way through. Well, what happens if I get the order received before I get the packing slip? Then you have all these different combinations, all these different edge cases that you have to consider. So so for me, what I like to do is take all of those individual details and just abstract them down into something that just keeps track of which ones depend upon which other ones, and ignore all of the others. For example, suppose that we're talking about a shipping system, and you have to place an order before you ship it. You have to have shipped the order before you can receive it. Okay, there's a causal relationship among those. But then on this other side, there's invoicing. You have to invoice an order. You have to place it before you invoice it. You have to invoice it before you pay it. Invoicing and shipping have no relationship with one another. They can happen in either order. So don't worry too much about those. Only focus on the causal relationships, those causal chains. And then you can limit the amount of interactions and edge cases that you have to consider. So if you need a bit more information on this, and I wouldn't fault you if you did, this is getting, this is just touching the tip of a really, really deep well. I am writing a book. It's called The Art of Immutable Architecture. And if you go to immutablearchitecture.com, you can sign up for a weekly newsletter. I'll be writing one article per week until the book is published, however long that might be. I am actually right now finishing up the draft of the very last chapter. I hope to get that draft to the publisher this weekend. And then there's going to be a year long of editing and all sorts of fun stuff. So during that year, then be expecting these new newsletters, and I'll get a little bit more deep into building distributed systems using ACID 2.0 and immutability. And so I really hope that you'll join me for that ride. And yeah, thank you so much for joining me with this dipping your toe into ACID 2.0. So get a few more questions in. We've got plenty of time to answer more questions. And while you do that, I do want to tease. We've got Craig Stuntz, a fellow software mathematician. He runs the Papers We Love group up in Columbus, and basically, like me, loves to read math papers and loves to see how we can apply mathematics to software correctness. He's going to be talking about shifting application security left. So doing your security analysis earlier in the pipeline and making sure that the things that you're building are going to be secure rather than trying to secure them after the fact. So keep yourself out of the news and come see Craig Stuntz talking about shifting security left. Do we have any other questions?
All right, I do have a few questions for you, Michael.
Mm-hmm.
The first one is going to be, let me get it back here. On ACID 2.0, are conflict-free replicated data types, abbreviated CRDT, a good example or use case for ACID 2.0?
Absolutely, yes. Yeah, because a CRDT is a data type that upholds some mathematical properties, associative, commutative, idempotent, and they are based on this idea of every time you operate on them, they move up in that cone, that causal cone. So everything that's in their future is in that cone. And so if you operate on a CRDT on two different nodes, you're going to get two different cones. When those nodes talk to each other, you're going to get that least upper bound. And that's where they're going to merge. Yes, CRDTs are the perfect example of semilattices and ACID 2.0.
All right, thank you for that. I do have an additional question here. Are there any open source systems that you would recommend looking into that may follow an ACID 2.0 architecture?
Oh, absolutely. So I'll go ahead and plug a couple that I work on. One is Correspondence. That's for C#. Haven't cracked that one open in a little while because that was primarily for making Windows Phone applications. Yeah, may it rest in peace. But the one that I do spend most of my time on now is called Jinaga, and that is for making progressive web applications using the principles of ACID 2.0. So yeah, in addition to that, I would say take a look at things like event sourcing. So there's a project called Event Store. There's another one. Goodness, I've forgotten the name of it, but it's like it's the name of like a little weasel or something. I'm blanking on the name, but that is a .NET event sourcing system that follows some of these principles. Key difference with event sourcing, though, is event sourcing doesn't demand that the application be commutative. The event stream is going to replay the events in the same order every time. And so the application doesn't have to be commutative, but then the flip side of that is you have to wait for an event to get into the stream to know what order it ends up in order for you to know how it's truly going to play with your system. So yeah, event sourcing is a good on-road to ASA 2.0. And if you want to go all the way in, I would say take a look at Jinaga and hit me up on Twitter, Michael L. Perry, and I'll help you out with getting started with Jinaga.
Great. An additional question I have here is, are you familiar with double entry bookkeeping? It solved many of these properties manually around 500 years ago.
Yeah, it's amazing. Yeah, people of the past, they kind of had it figured out. Yeah, so yeah, that is a perfect example. Is that if you were to take a look at what double entry bookkeeping is doing for you, first of all, accountants don't use erasers. So if they were to delete a transaction or modify a transaction, that could get in some serious trouble. So you only insert transactions, you only insert records. So that basically it means that double entry bookkeeping is a set. It's using set unions. So it's really taking advantage of those mathematical principles, and that's what makes it possible to reconcile your books with your bank at the end of the month. You know, what do I have that you don't have? What do you have that I don't have? Let's merge, and we come up with the same answer. Yeah, we can definitely learn from the past.
Thank you for that. I do have a few questions on your book. Is there any way to buy an early copy or get a preview before it publishes next year? And are there any other recommendations for more immediate resources I could get?
Okay, yes. So there will be pre-orders available as the date approaches, and that's, you know, to be transparent. That's really why I'm running the newsletter, is that that I really want to earn your pre-order, and so I'll definitely announce when pre-orders are open. As far as getting an advanced look at the view or at the book, I do need to talk with the publisher about that as things progress. But I'm working with A-Press, and they do a pretty good job of outreach. So I'm sure that could be made possible. In the meantime, a book that I got a lot out of. Unfortunately, I'm blanking on the name, but it's reactive. It's basically if you look for the reactive manifesto, from there you can find several different resources that are talking about distributed systems with the idea of using the reactive patterns in order to to come up with some really good solutions. So you'll find the architecture book that I can't recall the name of right now in if you do that search.
Thank you, Michael. I think that about wraps up the Q&A I have here.
Excellent. Yeah. Thank you so much for joining us today, and thank you, Michael, for for making this all possible. And I am really looking forward to next week hearing from Craig Stuntz. So tune back in.